On his blackboard at Caltech, Richard Feynman left a final aphorism: "What I cannot create, I do not understand." If we apply that standard to neuroscience, we encounter an immediate roadblock. Imagine trying to build a neural network from scratch that drives an agent to navigate toward a specific object, like an apple tree. To solve this, a researcher must bridge the distance between a foundation of code, whether genes or software, and a complex high-level behavioral output. Evolution complicates this. Nature selects for the final performance, the successful arrival at the tree, but the biological genome only encodes localized molecular mechanisms. The path from genetic code to behavior is mediated by self-organization. This internal process introduces a layer of autonomy that sits between the initial instructions and the final result. Because we cannot map the precise, shifting algorithms of this growth, we cannot explicitly program complex behavior strictly from the bottom up. In the early days of cybernetics, Francisco Varela described living systems as autopoietic, networks that actively maintain and organize their own structure. This self-maintenance limits the reach of biochemistry. Understanding a single molecular interaction in isolation provides no predictive power for how the organism will eventually behave in its environment. This is known as the levels problem. It is the primary barrier preventing researchers from extracting macro behavior from microscopic genetics. Information defined at the molecular level loses its explanatory weight after just a few steps of algorithmic growth. The initial signal is diluted by the cascading interactions that follow. Consequently, a deep understanding of a microscopic mechanism does not equate to an understanding of the terminal system. In practice, researchers in both artificial intelligence and biology solve the navigation problem by moving in the opposite direction. An AI engineer trains a neural network on an apple tree until it converges. A loss function adjusts the weights based on final performance, without hard coding how the network thinks. The AI succeeds, yet the programmer never maps the nodes that created this internal configuration. Developmental geneticists use a nearly identical strategy to engineer biological behavior. They perform a forward genetic screen. This involves mutagenizing thousands of flies to generate a population with randomized, unique genetic differences. These thousands of mutated flies are placed in a behavioral assay. The researcher simply keeps the few individuals that successfully walk toward the target and discards the rest. Both fields abandon bottom-up building. They generate random variation and apply a strict filter based on the final phenotype. To engineer a complex network, they intentionally bypass how it grew. If we isolate the one successful mutant from the fly screen, we can finally look at its code. The traditional expectation is to find a dedicated behavior gene that was programmed for navigation. Instead, the mutation often appears in a general metabolic enzyme, a protein that simply breaks down sugar for the cell's basic energy needs. This enzyme is used by every cell in the body for housekeeping. It has no specific instruction for brain wiring. During development, this mutation creates a sub-threshold change in the chemical environment of every growing cell. Most neurons ignore this slight change, using internal feedback to compensate and follow standard growth paths. But a highly sensitive neural circuit is pushed past a tipping point. It fails to compensate, rerouting its axons to a new region. This localized error triggers massive reorganization, resulting in a completely different wiring map. This unpredictable developmental cascade is what ultimately produces the specific, selectable behavior. Genes do not encode behavior directly. They encode the components of growth, and small modifications to those components steer the developmental algorithm toward new outcomes. This algorithmic model of growth was obscured for years by a major historical discovery made by Seymour Benzer. Benzer identified specific clock genes, where mutations mapped cleanly and directly to the timing of an animal's daily activity. The mechanism here is direct. The rising and falling of protein levels dictates the behavior in a simple, repeating cycle. Contrast this with the metabolic enzyme. The clock gene functions as a self-contained unit, requiring no complex developmental cascade. This is the Benzer paradox. The existence of clean clock genes created the expectation that all behaviors would eventually map to the genome this way. But in reality, these simple clock genes are a rare exception. Most behavioral traits are actually the result of highly complex developmental entanglements. When researchers assume every behavior must have a direct genetic map, they overlook the complexity that drives the majority of biological systems. Returning to the metabolic enzyme reveals the final limit of how much we can understand through reductionism. If we attempt to map every interaction in a developmental cascade, where do we stop breaking the system down? We face a combinatorics explosion. Breaking a mechanism into smaller parts increases the data points exponentially. Every step requires massive contextual information, and each component is constantly influenced by the feedback of others, making the system unstable and impossible to track. Mathematically, reconstructing this growth from the bottom up is intractable. This is why an AI's hidden layers remain opaque. The system works because of selection, not because we mapped the logic of its nodes. Defining a molecular mechanism gives us a static snapshot. It does not explain how information unfolds over time. To generate a complex system, biological or artificial, we must move beyond bottom-up control. We must learn to steer the unfolding algorithms of growth.